This is section 7.5, Trig Substitution. So when you look at this, you kind of get stuck. If you try a U sub and you look at this and you say, hey, let that be U, what happens? Let's see. Let U be 16 minus x squared. You find du, and that's negative 2x dx. And the problem is we're not going to get that there. Not going to happen. So now we're kind of stuck. Liate, that's really not going to work because you could try that. Let's see what happens. What other techniques do you have? You're kind of out of options. You're not going to be able to do partial fraction decomposition. So that leads us to trig sub. It's kind of a weird thing, but you'll see where this comes from. We're going to do a strange substitution that may not make sense, but I think will make sense as we start doing this. Magical things are going to happen. We're going to let x be 4 sine theta, and you'll learn later why that is such. But we're going to do some substitutions, but let's find dx first, and that's going to be 4 cos theta d theta, kind of like when we do a u sub, but now we're doing a trig sub instead of a u. And that's going to allow us to do some magical things. So first of all, we're just going to look at the denominator. Okay, if we look at that, we're going to replace x with that. And something cool is about to happen. So if I multiply this out, watch this. And even better, now they both have a 16. We can factor that out. And why that is significant? Because that's why we chose the 4 there, so that we can match the 16. So we're going to take the 16 out. Whoopsies. Didn't mean to do that. And hopefully, whoa, Yoshida, let's fix this. Hopefully, there we go. Factor the 16 out. And you should recognize that. That is cosine squared. That's a trig identity. So this becomes 16. Whoops. Try this again. This becomes, uh-oh, I am messing up. There we go, it's times. 16 cosine squared theta to the 3/2. Now this is the square root of all this, so that becomes 4, why do I keep doing that? 4 cosine theta, because we square rooted, cubed, which is, and I did not do all this, 64 cos cubed theta. So we are going to replace the bottom with that. So this integral becomes 64 cos cubed theta. And you might think, I'm still going to have trouble integrating that, but we changed things to theta. We don't want dx. We have to replace dx with dx. Just like in u sub, we need to get our variables to match. So the top becomes 4 cos theta d theta, and the bottom is 64 cos cubed theta. And nicely, one of these coses cancels, leaving a 2. So we're going to get, and let's reduce this. 64, that's 32/16. So now what do we have? We're going to have the integral of, and the 16, I'm going to take the 1/16 out, and we're going to have cos 1 over cos squared theta d theta. But what is 1 over cos squared? That's going to be secant squared theta. And the derivative of what is secant squared, you ask? Is it not tan theta? Whoa. Is it not tan theta plus c? So we think we're done. That's kind of cool, right? And it looks like we have an answer, but we have a problem. Our original variable was x. Our new variable is theta. We got to go back to the original variable. So let's take a look at this. I'm going to rewrite that. X equals 4 sine theta. Well, if I divide by 4, I get sine theta. There's a triangle associated with that. And from, not this again, from what you remember from geometry, the sine of an angle is opposite over hypotenuse. So opposite is x, hypotenuse is 4, right? Using the Pythagorean theorem, we get the missing side as 16 minus x squared. So just Pythagorean theorem. So we chose this to be our substitution. Solving for sine, we get sine is x over 4, but sine is opposite over hypotenuse. So this triangle relates to this. And using Pythagorean theorem, we find the missing side, and here's the deal. We want tan theta. If I gave you this triangle and asked you for the tan of theta, you would say opposite over adjacent, and you would do this. So therefore, we replace tan theta with that. And so we get 1/16 times, so the x is on top, and the square root of 16 minus x squared plus c. And that basically is our answer, beautifully. And we have used trig substitution to solve this integral. Well, how do you know you're going to be using trig sub? So here's a hint. The key is that. And the fact, remember in the process of doing that, we ended up getting just a cosine. So how do we do that? We did that by realizing this, if we pick the right thing here, became 1 minus sine squared, which we can use a trig identity on, right? So that's the idea that we're going to use. So if you see an a squared minus x squared, think triangle, think Pythagorean theorem. So how do you get that? This has to be the hypotenuse, that has to be a side, right? So a must be the hypotenuse, and x must be the side. And if we choose that triangle, opposite over adjacent is sine. So we could say sine of theta is opposite over, not adjacent, hypotenuse. If you solve for x by multiplying by a, you get that substitution. So it makes sense. When you have that form, you use this. Now the next one, when you think of that, a squared plus x squared, you should think, again, if this were a triangle, how do you get an a squared plus x squared? You should be thinking Pythagorean theorem, a squared plus x squared. So it has to be these two. Again, why a squared minus x squared? In a Pythagorean theorem, it's going to be hypotenuse squared minus leg squared to get the missing side. So if you want an a squared plus x squared, it's got to be the legs squared. Makes sense. And so if I gave this triangle and asked for the tan, you would say tan of the angle is opposite over adjacent. If you multiply both sides by a, you get this. And so that is a logical conclusion. If you have this form, try using a tan theta. And the last one is similar to the first one, except you switched your x and your a, right? The x and a are switched. So what do? Well, x squared must be the hypotenuse, and this must be a leg. And if you look at this, it's going to be cosine of theta, right, is adjacent over hypotenuse. Now, if you solve for x, using some fancy schmancy algebra, you end up with that. But what is cosine? That's secant. So we move to the top and make it secant theta. And so that's why you would use x equals a secant theta when you have that form. So these are the ones you have to recognize, and you think of a right triangle and the relationships, and it kind of just pops out naturally. Okay? So we're going to do one more example for you guys. Look at this. Did I mess up? Oh, I think I did. I wanted to do a different one. So on the fly, I need to fix this because I messed up. The bottom was supposed to be 1 plus x squared squared. So fix this. I'll probably, yeah. And this was supposed to be a squared. I'm so sad. I don't want to redo this video. Let me do this. This will be much better, cleaner. Let's do this. 1 plus x squared squared. That's what I meant to do, but I messed up. And make this fatter. Okay, you look at this form. That looks like a squared plus b squared. So you should think, which triangle would make that happen? And you should think that. Going back to this, a squared plus x squared, right? But your a is 1, so I probably should put, I'll just do equals 1. And so the relationship for theta would be tan theta is x over a, or x is x over 1. I multiply both sides by 1. X is tan theta, clearly, right? So that's my substitution, but let's find dx while we're here. Secant squared theta d theta. And now, let's do some side work. I'm going to replace x with tan theta. 1 plus tan theta squared. I substituted this into my x. I'm just working side work on the bottom. 1 plus tan squared. Do you remember what that equals? Let me remind you that sine squared, I know I'm forgetting my thetas, but I'm getting lazy. Cosine squared equals 1. If you want to get a tan, you sit out in the sun, or divide sine by cosine. So I'm going to divide both sides by cosine squared. And the first two get me tan squared. The second two get me 1. And the third gets me secant squared theta. So what is 1 plus tan squared? That is secant squared. So this is all secant squared theta squared, which is secant to the 4th. So let's go back to this original derivative, or integral, and replace the bottom with secant to the 4th theta. Now remember, we got to change this dx into a theta, but this is just secant squared theta d theta, and it's all coming into place. We see that those will cancel. Those will cancel 2 of these. And 1 over secant is what? You're right, cosine squared. Now, you probably don't remember, but this is a angle reduction formula. And we didn't really, I don't know if we did this last year. We may not have. But in angle reduction, let me do some work up here. We have some identities. We don't like the squared because if we try to do a u sub, we don't have the sign available and we're kind of stuck. So if you can change this using identity, we're going to do that. So we can say cosine squared minus sine squared was cosine of 2 theta. That was an identity that we had. And so we're going to use a form of this with only cosines. So we don't want sines. So we're going to replace the sine squared with 1 minus cos squared And again, I'm skipping my thetas. I apologize, just being lazy. I rewrite this. This will be 2 cos squared. I'll put it in. Minus 1. And if you solve for cos squared, you get cos squared theta. I add 1 to the other side, right? It's going to be cos 2 theta plus 1. Then I divide by that 2, and it'll be all over 2. That's just algebra. So all this gets replaced with that. So I'm going to do this equals cos 2 theta over 2 plus 1/2 d theta. This will be a u sub with u equal to theta. And when you do that, you're going to get sine 2 theta over 4 plus 1/2 theta plus c. And so that's the process of u substitution. You take something that's kind of strange, you use the, oh, I'm not finished, actually. Use the idea of a right triangle, and from there, you are able to integrate something that's kind of strange. Okay, so I'm not finished. So I need to change these thetas back into the original x. So I need to do some work. So how are we going to do that? We're in trouble a little bit here, but we're going to have to use some identities again. There's an identity for double angles. Sine 2 theta is 2 sine theta cosine theta. So I'm going to do that. It's going to be 2 sine theta cos theta. So what is that? Going back to ain't that beautiful? Going back to our original triangle here, I'm going to copy that. And so we have this triangle, and we had x and 1 and theta. Double check that. So the missing side is square root of 1 plus x squared using Pythagorean theorem. We want to know what the sine of this angle is. The sine is opposite over hypotenuse, and the cosine is adjacent over hypotenuse. So taking these two and plugging them in here will get me this. I'll work on the other pieces in a second. 2x over square root of 1 plus x squared. And this 4 is in the bottom, so I'll put that 4 there. And the cosine is that. So that's going to be 1 over square root of 1 plus x squared. And doing all my fancy schmancy work, I get x on top and 2 1 plus x squared on the bottom. Now we have to deal with that theta. What do I replace theta with? So let's take a look at our original here. Actually, this is 1. Let's take a look at that. If you solve for theta, so let me do x equals tan theta. We got that. So how do we solve for theta? Arctan. So arctan x equals theta. So we're going to replace all that with an arctan x. Arctan x plus c. That should have been up here. 1/2 arctan x plus c. And